Hello everybody, welcome back to the Graph Algorithms course. Today we're going to start talking about directed graphs versus undirected. In particular, talk about directed acyclic graphs and some of their properties. So, what's the motivation for this? The point is that sometimes we want to talk about the edges of a graph that have a direction. This is just because, sometimes pairs of things are related in a way, but the relation isn't symmetric. One of them comes before the other, or it's sort of a one-way viewership or something like that. And so we define a directed graph to be a graph where each edge has sort of a designated start-end and an end-end. So what are examples where we might want to use this? For example, if you've got a city map where lots of your streets are one-way roads, the direction that the roads point in is actually very relevant if you want to navigate the city. You can't just follow any series of roads you like because you'll be driving down some one-way streets in the wrong order. So you really do need to keep track of this orientation if you want to navigate the city. But also some of the examples that we gave. Links between web pages. The web graph is probably a directed graph because usually if you've got two web pages and A links to B, B probably doesn't link back to A. Similarly, if you have followers on a social network, it depends on the social network. In Facebook, friendships are symmetric, so they're sort of two-directional. That might be an undirected graph. But on lots of them, you can follow somebody without them following you, and so then you end up with wanting to have a directed relation for when someone's following someone else. A final example that we'll look at in some more detail today are sort of dependencies between tasks. So we have this directed graph, and we've already built up a lot of this theory that works for undirected graphs with the sort of Explorer and DFS algorithms. But most of this sort of actually still holds for directed graphs. We can still run DFS on a directed graph. The slight modification now is that when we run our explorers, we only want to check for directed edges out of V. So when we say for all neighbors W of V, if W has not been visited, etc., we really want to say neighbors where V points to W, not the other way around. And what this will do is it means that when we explore V, we find things that are actually reachable from V using the edges in the direction that they're intended. So we're only sort of allowed to follow these one-way roads in their appropriate direction. Now, using this new depth first search, we can still compute pre- and post-orderings. They still have many of the same properties. The algorithm for DFS still runs in linear time. Basically, everything's the same. The context is now a little bit more general. Okay, so let's look at a sort of specific example where directed graphs are important. In particular, suppose that we have the following morning routine. We've got to do a bunch of things every morning. We need to wake up, we need to get dressed, we need to eat breakfast, we need to go to work, we need to shower, all of these things. But we need to do these things in some order, but we can't do them in any old order because, well, we need to wake up before we get showered, and we need to dress before we go to work, and we need to eat breakfast before we go to work, and all of this stuff. And one way of representing these sorts of dependencies is by a directed graph. If we need to do A before we can do B, then we draw a directed edge from A pointing to B. And so this gives us some sort of dependency relation. And it's not just these sort of trivial examples of, how do I get dressed in the morning, but if you've got some sort of complicated system of libraries where some of them require other ones in order to work, you can end up with some sort of similar graph of dependencies, which you actually do need similar techniques to handle. Okay, so what do we do when we have these dependencies? Well, one of the things that we'd like to do is we'd like to find an ordering of the tasks in a way that respects these dependencies. We'd like to wake up before for example, suppose that we woke up at 7 o'clock and then showered at 7:05, got dressed at 7:15, had breakfast at 7:20, and went to work at 7:30. This puts all of our events in some order, and you'll note that this order respects all of our dependencies. We wake up before we shower, before we get dressed, before we go to work, and we eat breakfast before we go to work, and everything works out nicely. And so if we have one of these dependency graphs, we'd like to linearly order the vertices to respect these dependencies. Now, one thing to ask is it always possible to do this? And it turns out the answer is no. The sort of best counterexample is this following chicken and egg problem. I mean, the point is that you need a chicken in order to lay eggs, and you need eggs to hatch chickens. And so you can't like put them in some order where one of them comes first. If you put chickens first, then you've got this pointer from eggs back to chickens going in the wrong direction. If you put eggs first, there's this pointer from chickens back to eggs in the wrong direction. Without some place to have gotten started, there's sort of no way you can get this ordering going. In fact, in general, there's a slightly more complicated way in which this can fail to happen. In fact, if your graph has any cycle, a cycle here is a sequence of vertices, v1, v2 to vn, such that each one connects to the next using a directed edge. So you've got a bunch of vertices arranged in a circle such that each one connects to the next one all the way around. And the theorem is that if G contains a cycle, it cannot be linearly ordered. Okay, so just to make well, fine. Let's take a look at the proof here. So suppose that our graph has a cycle, v1 through vn, everything connected up in order. And suppose that additionally we can linearly order this graph. Well, if you linearly order these things, there are finitely many. Some one of them needs to come first. So suppose that vk comes first in this order. But now we're putting vk before vk minus 1. And vk minus 1 points to it. So we have an arrow pointing in the wrong direction, which gives us a contradiction. So if we have a cycle, we cannot be linearly ordered. So what this means is that in order to be linearly orderable, you need to be what's known as a directed acyclic graph, or a DAG. And this is just a name for a directed graph that has no cycles. Fair enough. Now, by the above theorem, it is necessary to be a DAG in order to linearly order. But one question we should ask ourselves, perhaps, is it sufficient? Can we necessarily linearly order it if it's a DAG? Well, okay, this is a question to ask a little bit later, but for now, let's just review. We have the following four graphs. Note that the edges here are sort of the same except for their orientations. And which ones of these graphs, or which one of these graphs, is a DAG? Well, it turns out that only A is. B has the cycle noted in red, and C has this other cycle noted in red. But if you work out A, you can actually see that it does not have any cycles to it. Okay, but the question that we were posing was, is it the case that any DAG can be linearly ordered? And the theorem that we'll actually show is that yes, if you have any directed acyclic graph, you can linearly order it. And next time what we're going to do is we're going to prove this theorem. But not just that. In addition to proving this theorem, we're actually going to make it algorithmic. We're going to come up with an algorithm that, given a DAG, actually produces this linear ordering. So that's what you have to look forward to next time, and I'll see you then.